One common application of exponential growth is in banking interest. So let's look at the compound interest formula. APR stands for annual percentage rate, also called the nominal rate, and it's the yearly interest rate of an account. If the interest is compounded more than once a year, and most accounts do have compounded interest, the effective interest rate is greater than a nominal rate. And you can tell how much is in the account by using this compound interest formula. So A of t represents the final amount in the account. P stands for the initial amount, how much you start with. R is the interest rate, written as a decimal. N is the number of times the interest is compounded per year. And there'll always be a word in the problem that tells you what N is. And T is the number of years that the money will be left in the account. So let's take a look at an example. If we invest $5,000 in an account paying 2% interest compounded quarterly, how much will the account be worth in 10 years? So when we see this word quarterly, that tells us that N is equal to 4 because there's 4 quarters in a year. Here we have our interest rate. As a decimal, 2% is going to be 0.02. 5,000 is our starting amount. That's what we'll put in for P. And our time is 10 years. So according to the compound interest formula, the amount in the account will be equal to our initial investment, 5,000, times 1 plus 0.02 divided by 4, raised to the 4 times 10 power. And so let's just go ahead and simplify this a bit, and then we'll get our final answer. All right, so 0.02 divided by 4, and adding 1. So here we have 5,000 times 1.005 raised to the 40th power. And if we do that, let's see what that would come out to be. We would have a final amount of $6,103 and about 97 cents. When will the account be worth $8,000? So we want the final amount to be equal to 8,000. So we would have 8,000 is equal to our initial amount. Notice that nothing in here changes, so that would still be 1.005 raised to the, but now in this case, we don't know what T is. We know the interest will be compounded 4 times per year, but we don't know how many years it's going to take. Now notice, again, this is one of those cases where our variable, our unknown, is in the exponent. And up until this point in our class, we haven't discussed how to solve this kind of equation. So we still have to wait a little bit longer before we can answer that question. Here's one for you to try. I'll help you get started. $10,000 is invested in an account paying 3% interest compounded monthly. How much will the account be worth in 5 years? So again, the compound interest formula, A of t is equal to P times 1 plus R over N to the NT. So in this account, we have an initial investment of $10,000. Our rate is 3%, in other words, 0.03, and compounded monthly means that N will be equal to 12, since there's 12 months in a year, and we want to know what the account will be worth in 5 years. Okay, so I'll give you a moment to do that on your calculator. All right, so when you did that problem, you had 10,000 as your initial investment, 1 plus 0.02 divided by 12, raised to the 12 times 5 power. And so you just have to do that on your calculator. So let's just go ahead and double check what you got. So we'll take that, we'll raise it to the 60th power and multiply it by $10,000. And so we have a final amount of $11,050.79. So that would be how much would be in the account in 5 years. Now the compound interest formula can be solved for the initial amount as well. A relative wants to invest in a college fund for a newborn child. The goal is for the account to grow to $80,000 in 18 years. If the account pays 7% compounded semi-annually, how much should be invested in the account now to reach the goal? So the compound interest formula, A of t is equal to P 1 plus R over N to the NT. And in this case, we don't know P. P is going to be our unknown value, how much should be invested. But we do know a final amount. The goal is for this account to have $80,000 in it when the child's ready to go to college. R is 7%, 0.07. Compounded semi-annually means it's going to be compounded twice a year. And so let's just fill in what we know so far. So 80,000 is what we want in the account at the end. We don't know what P is. We have 1 plus 0.07 divided by 2. N is 2, and it's going to be in 18 years. All right, so let's go ahead and see what we have so far. So 0.07 divided by 2. So here we have 80,000 is equal to P times 1.035 to the 36th power. So to solve this, all we have to do is take both sides of this equation and divide it by 1.035 to the 36th power. And that will tell us how much needs to be invested. All right, so if we do that, 80,000 divided by 1.035 to the 36th power gives us an initial investment of $23,186.62. So if this amount is invested now, the account will grow to $80,000 by the time the child's ready to go to college. All right. I'm going to let you figure this one out yourself. I'll help you get set up. How would the previous example change if the interest was compounded monthly? So everything else is going to stay the same, except now n is equal to 12 instead of 2. And so how would that change our initial investment? So again, it would start like this. A of t is equal to P times 1 plus the rate is still going to be 7%, but this time it's going to be compounded 12 times a year. So we'll have 12 times 18 years. So there's more opportunity for compounding. Why don't you go ahead and see how this affects P? All right, let's go ahead and check your answer. So if we do that, we'll have our final amount that we still want is $80,000 is equal to P times 1 plus, now this is an ugly decimal, so I'm going to just leave it as a fraction for right now. 18 times 12 is 1.18 times 12, let's try that again, is 216. So there's 216 compounding periods in this case. So to solve for this, we would take 80,000 and we would divide by 1 plus 0.07 divided by 12 to the 216th power. All right, so if we do that, divided by 1 plus 0.07 divided by 12 raised to the 216th power. That gives us an initial investment of $22,700 $775.55. So if the interest is compounded more frequently, you can see that it decreases the amount that needs to be invested to reach the goal.